So the starting point for this work is this well-known empirical phenomena that have been already mentioned a couple of times, is that for these modern learning algorithms, which are based on deep neural networks, they achieve their best generalization error in the regime where they fit the training data perfectly or nearly perfectly. And this is true even when the test error is far from zero, as in this sort of maybe a little bit extreme example from a paper of Nation Boer, where they show that sort of there's some kind of network. You look at different range of parameters, achieves its best. So the training error goes to zero. So the space where you achieve the best test error is where the training error is zero. And there are many examples of this kind of behavior these days. And the reason why this is kind of strange or puzzling is that, as you can imagine, most data sets, most natural data sets will have a non-trivial or at least a small fraction of outliers or noise. And there is no way for a training algorithm to actually predict the label on these examples correctly. So the only way to perfectly fit them is to effectively memorize the labels of this training data. So in fact, we know that even in these famous experiments of Zhang and others, that many of these standard learning algorithms will memorize even completely randomly labeled examples, such as in this specific case where they trained an inception architecture on ImageNet, which has 1,000 classes, and they trained it with random labels. And as a result of training, they achieved just 9% of training error, even though in this process, nothing has been learned, and the test error is essentially 100%. Obviously, it's exactly the chance of one. It's just the probability of guessing the 1 in 1,000 classes randomly. So obviously, it's not learning anything useful. The question is, why is this happening? So this question has been sort of brought into focus by deep learning, but it's not new. It has been observed by Peter and others in the context of boosting and bagging with decision trees, where again the best generalization error is achieved in the regime where the training error is zero, and that to me suggests that the sort of this phenomena might be even more fundamental than just learning with deep neural networks, and even and deserves even more understanding. So in addition sort of to intellectual interest, there are also practical reasons to understand whether this phenomenon, and they have actually just been mentioned by Caroline, and these come from privacy concerns. If you train your model on sensitive data about people, for example, their health records, financial data, location data, and you train an algorithm which memorizes, well, at least even just the labels of the data, publishing that model might pose privacy risks. And those are not theoretical. Again, you've seen examples of reconstruction in the context of autoencoders in Caroline's talk. But also just from in the context of classification that we're looking at here, there are a number of successful black box membership inference attacks on these standard learning algorithms, where basically just from looking at predictions of a model that has been trained, you can infer whether certain data points are present in the data set or not, and you can also fill in some of the missing attributes. You can easily see that this poses privacy risk in many contexts. So this sort of practical reason poses a very concrete question. Is this kind of memorization or of labels, is it necessary for achieving the optimal error? In other words, is this some kind of artifact of our training algorithms that we're using, or something fundamental to learning? Can we possibly maybe achieve the same accuracy, but without being in this sort of zero error or very large sort of amount of overfitting regime? So now let's look a little bit at what the current theory, what is the current state of the art in understanding this question. And for this, let's start with sort of the most basic way of understanding a generalization error of an algorithm. Let's say our algorithm outputs model H hat on a data set S, and we want to understand the generalization error of this algorithm, which is denoted by error with respect to the underlying distribution P of H hat. we start usually by decomposing it into the empirical error part, something that we can easily measure, and the difference between the empirical error and the generalization error, which often is referred these days as generalization gap. This is, again, a measure we cannot directly compute, but we can control it or bound it via various proxies, such as VC dimension, margin, norms, so stabilities, and that's sort of what a lot of learning theory does. Maybe a concrete example is that if we know that the model H is belongs to a class of binary classifiers capital F, then this generalization gap will be upper bounded by twice the empirical Rademacher complexity of this class F on the data set S plus some kind of sampling, essentially sampling error. So this standard decomposition suggests that what learning algorithms should be doing, that they should be balancing some kind of the empirical error or fit to the data, and some kind of regularizing term which controls this proxy. So it has been already mentioned that this doesn't seem to be what's happening in practice, at least in these applications. Their algorithms are very eagerly memorizing noisy data, which again doesn't look like balancing fit to and regularization. But also on the just purely theoretical models, we know that all of our bounds are conservative, and in order to and anytime you sort of and to memorize every single, say, noisy examples, the measure that we control will grow by much more than our gain in the empirical error. So just immediately from this constant 2 that we have, we know that we'll pay the price of at least twice as much in our upper bound on the gap than what we'll gain in the empirical error. So this is all to say that the sort of existing bounds do not explain the behavior that we see. And this is in the best case. In the worst case, they actually suggest that whatever we're doing is actually suboptimal. We shouldn't be doing this. And we don't believe that that to be true. So let's discuss a little bit some of the other related work about which was motivated by this topic. So perhaps the closest is this, now this guy could say an area of understanding generalization of interpolating methods. And as you know, interpolating methods are methods which fit the data perfectly. And it started back in the 60s with the classical work of Cover and Hart for 1 year's neighbor, and has received a lot of attention in just past couple of years. And that's the work that Peter has talked about. And the upshot of this work, maybe in Peter's words, is that it's not a crazy idea to use an interpolating method in some contexts. In fact, there are ways to analyze interpolating method which shows that they are maybe not much worse or comparable to methods which do not interpolate. But from our point of view, this doesn't answer the why question. So is this actually necessary? Because it assumes the interpolation as given and just studies its property, but why should it be there? We do not know, and none of these results show any sort of advantages of being in this interpolation regime. In fact, the results are usually somewhat worse. In addition, we know that overfitting also happens, or this memorization of labels also happens without interpolation, both in practice and theoretically. For example, that example for ImageNet, we only reached the 9%. Training error, not 0%, but still have memorized over 90% of the labels. And let me see what I mentioned. Yeah. So again, so it's, and one can also interpolate without memorizing. If the model is very simple and you have enough data, you can actually just fit it without have a sort of zero error, but not you don't need to memorize any of the labels. So it's effectively a somewhat different but related phenomenon. So some of the work which is kind of motivated by this question demonstrates benefits of over-parametrization. And now we understand those relatively well. Sort of over-parametrizing the model gives us access to a richer class of models. And sometimes it's easier to, we know that sometimes it's easier to optimize over this richer set of models. But over-parameterization by itself does not allow you to fit the data perfectly, but it doesn't imply it. So basically, it's not just because you can, it doesn't mean you should be doing. Finally, let me mention that there is some work which suggests that interpolation might have some computational benefits, and this is based on analysis of stochastic gradient descent for convex models, where if all the loss functions have a joint minimizer, the rates that you'll achieve will be better. However, there isn't that much evidence for this kind of computational advantages in the context of training deep neural networks. And in fact, we know that in many, so while there are examples where we reach this interpolating regimes, in many of the state-of-the-arts, the results are actually not interpolated, because in many of those results, one uses various data augmentation techniques, which kind of implicitly increase your data set by adding to every data point various sort of rotations and shifts. So your data set becomes effectively much, much larger, and that kind of implicit data set is no longer being fit perfectly. So as I said, this is sort of not necessarily, we're not necessarily in this interpolating regime in many of these cases. So now let me go and kind of present sort of the most basic idea of the explanation that I give in this work. And I'll do it by one slide, which is kind of based on a true story. And that true story is trying to, again, just classification on the standard CFAR10 dataset. And let's look at 4 examples of or actual examples of the truck image from that dataset. It's one of the classes. And what's sort of special about these 4 examples is that they all, basically none of them would be predicted as a truck if you were to remove them from the dataset, which means that in order to fit any of those examples, the algorithm, again, needs to effectively memorize the label, because it won't know that this is a truck. And and these examples are all very different from other examples of truck. So the question, should a learning algorithm memorize any of those examples? And it turns out it's not, at least certainly not obvious to me, but it turns out that in some sense memorizing this one is useful in the following sense. If we were to ignore or remove this point from the data set, the resulting accuracy on this particular test set image would be lower. For this image, there is no observable effect on the test set error, so probably it's useless, at least as far as test error is concerned. For this example, it is, again, useful. It helps increase accuracy in predicting on this test set. And finally, on this one, it is, again, this is not useful. But the point is, so the point is that there are some images which are useful to memorize. However, a priori, without kind of observing, knowing anything about the distribution, if you only the only thing you know about trucks is what you have seen in your training data set, you might not be able to tell these useful images from these outliers or useless images. And as a result, you will be memorizing, if you want to make sure that you get the benefits of accuracy on the useful example, you will also be memorizing the useless ones. So that's at a high level. Now let me just try to make this a little more concrete and formal. And for this, let me start by explaining what do I mean by a rare. And the best way to sort of describe this is by sort of realizing that most natural data is not sort of homogeneous Gaussian. It's better thought of as consisting of subpopulations of different subpopulations, which are quite different from each other. For example, if you consider the class of birds in the CFAR10 data sets, again, actual images, they consist of images of hundreds of different species of birds, taking at different magnification levels, different body parts, different backgrounds. And again, if the only thing you know about the dataset birds is what you saw in this dataset, they all these subpopulations do look very different in the sense that if you don't see any of the representatives of a certain subpopulation in your dataset, you might not be able to predict accurately on that subpopulation. And because there are so many different subpopulations, some of them will have relatively low frequency in the data distribution. For example, accuracy on the order of 1 over n, where n is the number of samples. And for these subpopulations, you'll observe roughly one example in the entire training data set. And that one example is also the number of examples you'll observe any outlier. So effectively, you will not be able to distinguish something which is useful, has probability roughly 1 over n, from something which is complete outlier, might have a probability of 1 exponentially small probability and completely useless. But it, again, occurs only once. And similarly, when you have very low confidence in a certain area, you would not be able to tell a noisy example from correctly labeled one. So as I said, these examples from these low frequency subpopulations may be hard to distinguish from noise and outliers. Now the question, are these relatively low frequency subpopulations, are they important for the overall task of prediction? And that depends on the kind of the distribution of frequencies of subpopulation in the data distribution. And many have heard, you probably heard this expression that natural data tends to be long-tailed. And one sort of important property of long-tail distribution in this context is that, such as, again, power law or zip distribution, is in this distribution the total weight of frequency on the order of 1 over n ends up being a significant fraction of the whole population. For example, in the prototypical long-tail distribution, the zip distribution, which and we'll take over capital N elements, and the zip distribution is the one in which the kth most frequent element has frequency proportional to 1 over k. So we know that for this distribution, the total weight of frequency on the order of 1 over n is on the order of 1 over log capital N. And capital N is the number of different, again, subpopulations in this case. So it is a significant fraction of the entire probability mass. Okay, so that's a bit of an anecdotal evidence. It turns out that there are some papers which show that this is not just a sort of anecdote. This distribution actually happened, and they come. One of this example comes in the context of data sets which have additional annotation. For example, there is a SUN data set which is annotated by so-called, in which every image is annotated by the visibility pattern. What is the sort of angle from which you see the object that is being identified? And they plot the number of objects which have a certain visibility pattern. For example, this for a bus, the most common one is that's how you see a bus, and one of the rare ones is this is how you see a bus, and similarly for a person. And it is clear, I mean, if you look at the log plot, that, for example, this distribution is basically a zip distribution up to a bit of error. So that's one example. Another context in which it is known the data follows long-tail distribution is these extreme multi-class problems, for example, in text categorization. And in these problems, we have a huge number of classes, often hundreds of thousands. And the number of images you have or text sentences you have for each class is not the same, like in the standard benchmarks. And in this context, people often look at how many images you have per class. And here is an example for Wikipedia data set, which has 300,000 different classes. And this Amazon data set, which has 670,000 classes. This is, what this plot shows on a log linear scale is that the number of images per class is, again, roughly a zip distribution. And to connect it to the subpopulation of a single class, it suffices to notice that in this extreme classification problems, each label corresponds is very fine-grained, and many sort of instances of these fine-grained labels correspond to a single coarse-grained label in other data sets. So, like, imagine again having a dog and different breeds. The fact that we have this long-tail distribution in fine-grain distribution means that the distribution of subpopulations inside a coarse-grain label would be long tail. So anyway, so this is just to convince you that these long tail distributions exist. The question is, how do we convert this intuition into theoretical models? And as I'll show, it's actually not that hard to do. And to do this, I'll start with a very simple kind of simplified models whose goal is to just capture sort of the essence of the phenomenon here, that you cannot distinguish things whose frequency is 1 over n from outliers, things which have frequency much lower. So the goal is to design a learning model in which, as a result of not being able to distinguish, you will be forced to kind of fit fit the data. So let me start with describing the model. It will be very simple. We'll have some discrete domain X, which will have size capital N. So each point kind of corresponds to a subpopulation. But in this case, it's just a discrete single point. And we'll have some distribution D over that domain. And we'll also assume that there is true labeling function f, which belongs to a class capital F, again, which is for M class classification problem. You can just think of a binary case. It's not very important. As usual, we'll be trying to understand how to minimize the expected generalization error of an algorithm, which is just the expectation over a data set drawn randomly from this distribution which labels the data with f, and the model output by the algorithm of the generalization error. So far, everything is standard. What's new is that we will explicitly assume that these frequencies follow a certain distribution. For example, long tail, but for simplicity, we'll assume that any distribution. We'll phrase things in a general term. So we'll assume that there is some kind of, we'll call it prior over frequencies, which is described by pi 1 through pi n, just a vector of frequencies. And what we'll assume that is, before you observe examples of a certain point, of a certain data point, you basically know nothing about its frequency. So, and to express this, we'll think of the following kind of generative model, which expresses this assumption, in which we'll define basically a distribution over distributions in the following way. For each point x in our domain, we'll pick randomly and independently one of those frequencies from this prior. And then because we want a distribution in the end, we'll just normalize those to 1. And this, again, expresses the fact that we basically, the only thing we know is that the distribution will follow this long tail, or at least a long tail set of frequencies. And the frequencies themselves are independent. You don't know anything about it before you actually observe any examples. So now we'll define the sort of the goal of the algorithm will be to minimize the expected error of an algorithm. So which will denote this, but this bar r n for an algorithm A, which is just the expectation of the generalization error, where we take an additional expectation over our sort of data generating this distribution, or model generating distribution, where we pick the distribution according to this process. And for simplicity, we'll also assume that the function itself is chosen randomly from the class of function. That is actually not very important. We can replace it by worst case over f. But for convenience, it would be easy to just put everything in one expectation. And so this is the error that we would like to understand for an algorithm. And specifically, we'll want to compare this error to the optimum achievable by any algorithm, which has access to n sample, which will denote by optimum, again, which will depend on the prior pi, and again, a class of function, which is just the minimum over all algorithms. Easy to see that this minimum is achievable by an algorithm. And this choice of sort of comparing ourselves, we'll be comparing ourselves to this optimum. And this choice of optimum is important because, in principle, one might be, we're looking at distributions which are realizable. There is a function, there is a labeling function which will achieve 0 error. There is no underlying noise. But there is no algorithm. For many classes, there will be no algorithm which actually can achieve this 0 error. And when you compare yourself to something which, I mean, maybe a standard point of comparison is the best model, what we do in learning theory. When you look at comparison to the best model, even a small factor difference in the comparison, for example, you lose a factor of 2, and you get the error which is twice as large, it can completely kind of erase all the finer distinctions that might be determining what we are doing in practice. And that's kind of the phenomenon that we'll see in a second. So, OK, so that's what we'll be doing. And the main result for this simple model can be summarized in the following way. And it's like a special case of the result, but it doesn't matter. What we'll show that for every algorithm A, it doesn't matter what the algorithm is, its sort of expected error, as we defined, is lower bounded by the best possible, by the optimum, plus some term, which is basically just the same expectation here, expectation over the data generating process, expectation over the data set. But now we'll be looking at this term is the number of examples which occur only once in the data set S, but are not fit by the specific model H, which is output by the algorithm. So we're basically relating the error of the algorithm. We express the suboptimality of the algorithm in terms of the number of examples it doesn't fit. So there is some kind of multiplying factor here, which will determine how strong this suboptimality is. And this factor, it's not very important what it is. It's actually some kind of, you could think of it as some sort of Bayes update factor, which shows you, having observed an example, say, once in this case, how likely, what is the expected probability of that example under our data generating distribution. Most importantly, it depends only on the prior and the number of examples that we have. And it's easy to estimate. In general, it can be lower bounded by the total weight of the frequencies on the order of 1 over 2n. Sorry, on the order of n. In fact, it also can be also upper bounded by this weight. So if there are no frequency on this order, then suboptimality will be very small. And as an example, for the zip distribution, this suboptimality will be 1 over n times 1 over log n, where 1 over n is just the normalizing factor, because here is the number and this is the error. So it will be effectively, for every example you do not fit, you'll be paying roughly 1 over log n in your generalization error. So it's a significant cost. And maybe it's worth noticing that actually for this result, the class of f that happens is actually not important. It doesn't matter. It doesn't play any role. The moment, if you don't fit, you'll pay a price. But the class of f will matter once we start talking about memorization. So first of all, I haven't formally defined what do I mean by memorization, specifically label memorization. And it's defined in a very simple way. We'll measure memorization of an algorithm, memorization of an example Z, which is in data set S, as the difference in the prediction on that example when the example is in the data set and the example is removed from the data set. It's basically some kind of leave one out stability, but it basically just measures how much the presence of the example affects prediction on the label of that example itself. So if there is a large change in the prediction, we say that it's kind of memorizes, and we quantify it by this difference. Now, with this definition in place, it's actually very easy to connect this memorization to our result. And in the following way, I'll state it mostly informally. If we'll have a sufficiently hard or rich class of function to learn, then for many examples in the data set, we know that the probability that the model predicts correctly the example without observing the example itself is much smaller than 1. Just this follows immediately from the fact that that leave one out error is essentially unbiased estimator of the true generalization error. If generalization error is relatively high, then there will be lots of examples for which the leave one out, if you leave them out, you will not be able to predict them. And these examples, in order to fit them, you need to memorize them just by this definition. I mean, if your prediction is low, in order to fit, you'll have to pay the price of memorization. And so we can, in this way, can relate memorization to suboptimality, because fitting Again, if you don't fit, then you are suboptimal. The algorithm will be suboptimal. Okay, so that's a brief summary of the sort of the most basic result. Let me briefly describe. So for now, I've been talking about just about this discrete domain, and it's maybe not so clear to you how do you relate it to sort of the continuous world in which every predicting fitting at any individual point is not even that important because it has essentially zero mass. It will extremely unlikely to occur again. So to extend it, the extension to this more continuous world is very easy. Basically, we will now, instead of having this discrete set of points, we'll have just capital N different distributions, each distribution representing one subpopulation. And we'll have some true labeling function, which is constant over subpopulation. Again, subpopulation are subpopulation of a single class. So the labeling function is constant over those. And now we'll define, the data generating process in essentially the same way. For each index I of a subpopulation, we'll pick randomly and independently the frequency, and we'll normalize these frequencies to 1. And the data generating distribution is defined just as the mixture distribution where sort of with these frequency coefficients, where instead of individual points, we have just this distribution corresponding to a subpopulation. And as before, we'll want to minimize this expected error, again, defined in exactly the same way. So now to relate, so this will be the problem definition. Now, in order to be able to kind of convert our results for the discrete setting into this continuous setting, we'll need to assume that the algorithms do not behave arbitrarily in some sense over all points in the subpopulation, because you have to assume that there is some, there is something that we call coupling, and it's defined very easily, very simply. We'll say that algorithm A is lambda subpopulation coupled if the following condition holds for any example which occurs once in the data set, example which is the only representative of some subpopulation, the prediction that the algorithm makes on that sole representative of subpopulation is in some way close to the average prediction on that subpopulation. So, and how close it's measured is at most 1 over lambda in total variation distance. So so basically assume some kind of correlation between those two. And once you make this assumption, our main result is easy to translate to this setting. You basically just lose this additional lambda factor, which depends on the strength of coupling. It's all abstract, but actually it's pretty easy to show that this kind of coupling naturally happens for many algorithms. So for some like nearest neighbor algorithms, it's easy to see because the point are, you assume that the points in the same subpopulation are closer to each other than to other points. Then you observe the first point in the subpopulation. It's likely to affect how you label the entire subpopulation. And similar things also happen for sort of when you look at large margin classifiers or SVM in over-parameterized regime. There again, you will be labeling. If you think of points in the subpopulation as being close to each other, maybe clustered around some point, once you learn some large margin separator, you're likely to label the points in the subpopulation in a similar way to the member of point, at least because again you'll be cutting at least of the one half of the half space will be on the same side of the classifier. And you can find the details in the paper. It's not very important for these purposes. So that's all that I wanted to say about the theory. Let me now talk a little bit about the experiments that, as I have mentioned, are with Chiyuan Zhang. And there we're sort of testing you could say the main hypothesis which comes out of this theory is that there are these, you can find pairs of examples which are kind of, we think of them as belonging to the same subpopulation, which means that they should be visually similar. And they have the following property that sort of the example in the training set needs to be memorized in the sense that I have defined that if you were to remove it, you won't predict it accurately. And this example in the training set has each of those examples in the training set has a significant effect on the accuracy of the corresponding example in the test set. So we formalize it as this definition. We were saying that there will exist pairs of examples, one in the training set and with a test set, needs to be memorized. So at least the difference in the prediction, at least some 20%. And the example in the presence of the examples in the training set improves prediction on the test set by, again, at least 20% for concreteness. And we also, of course, need to show that there are many examples of this kind, because otherwise the total effect of these examples will not be significant. So that's a nice hypothesis. The main problem with it is actually basically actually evaluating this hypothesis, finding all the examples of this type, is computationally prohibitive. Basically, it requires you doing leave one out training. And as had been mentioned by Tamara, that's again, this requires a huge number of executions. And for example, for something like some simple data set like MNIST, actually verifying this directly would require over millions of runs, just because there's also additional randomness in training. And that's computationally prohibitive, even if you have access to some Google clusters. So the question is how one can do it, how to find these examples, which we call them too long tail. And what they show that there is actually, OK, so on the experimental side, our main contribution is to show that there is a relatively simple way to identify these examples. And we do it in the following way. What we do is we generate many random subsets of the training set of size roughly, say, 70%, but it's not very important. And we'll train on each of those random subset a model. And then we'll, for each pair of training and test example, we'll be computing the advantage, sort of relative advantage that that including that training example in the data set. So some of the random subsets will include that training data set, some will exclude. We can compute the average accuracy on those that include versus those that exclude, look at the difference. And that's what we call advantage. We'll sort by advantage and pick those which are sufficiently large ones. And what we show that in this case, to get a lot of candidates, it suffices to maybe have just a couple of thousands of runs, which is still not very cheap and kind of somewhat constrains us in terms of the kind of algorithms we can try this on. But we were able to do it on many of the simpler benchmarks. And let me show you some of the results. So let's start, of course, with the venerable MNIST data set, which has like about 50,000, oh, not about 50,000 training examples, 10,000 test examples. And here, sort of you could say almost baseline accuracy is over 99%. So in some sense, there are very few examples which need to be memorized. This is already, there's very little at play here, but still, using our technique, we have identified, for example, this is the ones where the advantage is the largest. Again, this is an example from the training set. This is a corresponding example from the test set. It's makes a lot of sense why this memorization of this example improves accuracy on, for example, on this one. In effect, no other examples, and similarly for the other ones. Here, advantage is over 30%. If you go down, you still, again, things align make a lot of sense. You find that these couples exist. And further down, the difference becomes a little larger, but still, it's clear that there are these kind of very special and rare ways to write digits so that you won't be able to predict them well unless you have something very similar in your data set. So these kind of subpopulation exist even in the ways people write digits. So these were identified using our sort of method, which is not exact, but we then verify how much advantage does it give in this leave one out world, and we find more than 70% examples where advantage is more than 10%. 70 doesn't sound much, but again, there is only 1% of the test set at play. It's only 100 examples, so it's not a small number of things we find. So now let me also briefly describe you some examples on CIFAR 100. Here we have, again, still 50,000 training examples, but now over 100 classes. So there are many fewer examples per class, which does, according to sort of our calculation, put many more of the examples in this tail. So after running, here are some of the results we found. So the ones which are most influential, somewhat unsurprisingly, are hard examples, which are also near duplicates. And that's maybe one of the artifacts of the older data sets like CFAR, that they actually have a lot of data sets. That's a good reason to memorize something if you're really likely to be asked exactly the same, or almost exactly the same question again. So maybe it's not the most exciting reason, but OK, this is what one should be finding first. If once you go down the sort of advantage, you start seeing maybe examples from different sets of images. Maybe are not quite identical, but they have again, clearly related in some ways, like a same frame of the adjacent frames in video. And as you go further down, you see even more kind of clear generalization. These are, again, harder. These are all kind of unusual examples of each of those images, but ones in which you having the example in the test set is useful. All in all, we find over 700 examples with more than 10% advantage. And 700 examples is about 7% of the test data set. So you can see in this case, it's the overall impact of this memorization is certainly significant. So that's all that I want to say about our experiment. Let me briefly mention some more sort of supporting evidence or experimental evidence that existed before our work. And that's this is work that looks at training models with differential privacy. And it's not so important what the definition is of differential privacy for the purposes of this talk. But this definition by itself prohibits the training algorithms from memorizing or overfitting. So as a result of these models will be models which do not overfit. Basically, the test and train will be the same. And again, they do not memorize. So it's very nice, very good for privacy, but there is a cost to it. For example, we know that the best algorithms that have this property for a reasonable value of privacy will have the error of around 2% on MNIST, as opposed to just 0.2% non-privately. So there is a cost. And some of this cost is probably due to the fact that we don't have the best algorithms, differentially private algorithms yet. But I can check here that some of this difference is kind of inherent. Because you don't memorize, you will be losing out on accuracy. And the evidence for this comes in sort of in this work that I want to mention, which looks at the examples which are predicted accurately by non-private, by models which are trained without differential privacy, but are not predicted accurately or by differentially private models. And here they're arranged by those on which the differentially private models are least accurate to the most accurate. And again, you can see that the ones which are least accurate are all these really weird ways to write the digits. They're sort of very unprototypical, those which occur very rarely. And the ones in which they are accurate, you get them there. That's where you are the most accurate. And they do it for many other data sets. This is, for example, an example of for the planes. And again, a really similar situation. So that's another bit of evidence for the need for memorization, and one that actually inspired some of this work. So now let me conclude by briefly summarizing. What I wanted to convince you is that this kind of extensive label memorization or overfitting is not well explained by existing work. It doesn't provide the answer to why is it there. I believe that the reason for this is the sort of the fact that the natural data has this long tail distribution, which forces the algorithms to kind of memorize. And the sort of upshot of this model is that this memorization overfitting is necessary for achieving optimal generalization for these long-tailed distributions. The more details can be found in the paper, which is now on archive. And in terms of future work, I mean, of course, the hope is that it will lead to more faithful theoretical models. And in my view, sort of one of the reasons why the theory is relatively stuck in its progress on understanding deep neural networks is the lack of good models of data. And the hope is that this will help to get better models of data. Of course, eventually we want to make sure that this translates into better design of practical algorithms. And with also this work has interesting implications for privacy, or for understanding of privacy and limitations of learning with privacy that I also think are important to explore. That's it. Let me know if you have any question. Thank you.